Good morning. My name is Donald Sheppard. I am the laboratory manager for QRS Calibrations. Uh, Dave Heiselt's right up front here. He'll be chiming in from time to time because I sometimes go a little too fast. So if any time during the conversation today, if y'all have any questions, please feel free to ask. I've asked that they're at the end. We have a time for questions at the end, but by all means, if there's something right up on the slide and you want to ask a question, just feel free to chime in and ask a question. So today we're going to cover back to basics of measurement. So metrology, calibration, and biomedical, we both operate in the same world. We tend to use some different terminology, and some of the things that we look at in a calibration lab versus what you're looking at in a biomedical shop, they're interactive, and we want to be able to provide some information on how you can look at things from our perspective. So when you have an issue, you can let your laboratory know what you're looking for. We're going to cover some of the terms and definitions we use in the calibration lab, the different reference standards. And when I'm saying standards, I'm talking about the publications, documents, difference with accuracy and traceability versus your published specifications for your test equipment, some of the different things you can look at for your quality of measurements, and then discuss, again, your partnership with your calibration laboratory. Then at the end, we're going to have a practical demonstration. We have some different temperature measurement devices up here, so you can look and see how each of them respond differently and measure differently, even though they're all measuring the same thing. So, as I said, Dave Heiselt, go ahead and introduce yourself.
Thanks, DJ. So I'm Dave Heiselt with QRS Calibrations. We've been in business for about 15 years, providing both mobile on-site calibrations, primarily to biomeds, third-party service companies, and medical device manufacturers. If you have a scope of capabilities, it really doesn't matter who the customer is, but we've really carved out our niche in providing metrology to healthcare. In the last several years, we've also gained our accreditation for 17025, which is a metrology standard. And in doing so and working with our hospitals, we're finding that there's some gaps with healthcare that ultimately biomeds don't see themselves as metrologists. But by definition, metrology is the science of test and measurement. And what do biomeds do every single day? Test and measure. So by definition, biomeds, or at least our field of biomedical engineering, are metrology fields. So with this definition behind us, we've also seen that there's some basic fundamentals of metrology that are not being taught in biomed programs as we know them. These are just general practices for traceability, accuracy, readability, the core things that you should know when you're doing anything test and measurement wise. So once we saw this, we communicated with a lot of our healthcare organizations, both large and small, and said, hey, is there really a need to come out and do some further, foundational training for metrology practices for biomeds? And overwhelmingly, it was yes, we really could use this. So we've now made it our mission to come out and share with the biomed community as we know it, to backfill in a lot of that basic metrology practices that should aid you guys in your day-to-day test and measurement. Today, we're going to be kind of looking primarily at temperature, but it could be anything from AC/DC volts, AC/DC current, resistance, temperature, mass. I mean, you name it, we work within it in biomed, and that same practices apply. So that's kind of what our mission is now, is to come out and partner with healthcare in understanding how we play an integral role. And there is, I want to point out, a new standard that's coming out for healthcare metrology. Currently, it's primarily being dominated by the labs as you know them. So Abbott and some of the other big laboratories out there, they're playing an integral part in developing these standards for metrology practices. But ultimately, I think it's going to be applied across the board to biomed as well as laboratories. So we want to see more biomeds get involved so that you have a say. I'll give you a great example. When DJ and I found out last summer that this healthcare group within metrology was being formulated, some of their guidance documents said things like the uncertainties to consider, and they listed off 5 or 6 uncertainties of temperature, humidity, and things like that that only really applied to laboratories. Well, that made sense because the laboratories are the ones spearheading the healthcare group as we know it today. So we got the language stated that it's some uncertainties to consider, because in biomed, we'll have a lot of other uncertainty factors to also consider. So we didn't want to guide people that these were the only uncertainties that you'll have to take into consideration. So just as an example, we want to make sure that you guys are well aware that these types of organizations and guidance documents are currently being formulated, and that you need to get involved. If you don't mind having it just handed to you and you're going to do this, then don't get involved. If you want to have a say in what these documents and guidances are all about, come see us at the end. We can provide you information to get involved so that you have a say in what these documents will do for biomed, healthcare, and metrology. So again, thank you.
All right. So I have 27 years in metrology. I started off in the Air Force metrology and calibration program. I've worked for the FAA National Test Equipment Program, doing aerospace, radar, and communication work. I also spent a couple years as the chief measurement scientist at NASA Wallops Flight Facility before I moved over to QRS Calibrations as the lab manager. So we're bringing together many years of experience working with this stuff from different aspects. And again, that's where we found out that all of this comes together. So some of our different references that we use in a metrology and cal program, NIST traceable is not one of them. NIST is not a reference. They're a national laboratory, but they are not a reference for what type of calibration you want to get. For calibration, our pinnacle is ISO EC 17025. This is where we take into account all risk factors in a calibration. 17025 is an accredited calibration. They have to come in, verify our technicians are doing things correctly, verify our quality systems operating. And then we have to do intercomparisons with other laboratories in our same scope of service. So all of our work that we do gets compared against Fluke or a NASA calibration lab or just other labs. And we have to pass those proficiency tests to maintain our accreditation. Of course, ISO 9001, your general quality management system. ISO 10012 is your basic metrology calibration program. Then you have your ANSI Z540s. These are how you report data to your customers. You got SAE AS 9100, which is an aerospace document about how different aspects of the materials and the calibration all work together for safety, including foreign object debris inside the equipment. And then you have your joint committees guidance for metrology, 100, 200. These are your the international standards on this is how we take a measurement, and this is the terms we use for measurement. NCSL RP6, this is the recommended practices for healthcare metrology. And then this QM1, which is how our national quality system works from NIST down to the secondary laboratories. So metrology is the science of measurement and its application. So metrology is specifically just how we look at a measurement. It is not the actual calibration itself. It's not the performance test. It is just all the factors that go into a measurement. So if we were to measure temperature in water, we would be looking at, okay, what is the chemical makeup of the water? Is it distilled water? Is it just tap water? You know, what is the ice mixture to the water itself? What type of probes are we using? What type of reference meters are we using? All of those things will tell us how small and how accurate and how reliable that measurement is. Calibration is the comparison of one known reference to an unknown reference, and it's only for that one specific point. That is that calibration. So we're taking our ice bath here and we're measuring it with different probes, but that is the comparison, is that. So calibration is just the comparison. It is not the adjustment. So at their core, both metrology and calibration are focused on ensuring measurements and measurement data are adequate for the intended purpose. So when you send your stuff off to a calibration lab, you want to make sure that you tell them what you're actually looking for. If you just send it into the cal lab and say, hey, I just have this meter, I want it calibrated, they're going to give you the same cals they give everybody else. But you might use that device differently from the general user. So you need to let the laboratory know what you're looking for. So some of the different metrology terms and definitions. We have true value versus indicated value. So the true value is that the fundamental atomic equivalent of what that measurement is. And at our level and at your level, we will never know what the true value is. The indicated value, that's what you're actually seeing. So calibration versus a PM. Biomed, you guys use PM all the time. Believe it or not, it's the same thing in our lab. We just call it a calibration. For us, a PM is the filter clean. But when we take the measurements, that's the calibration or the performance test. So the performance test is the series of calibration steps to get to whether or not the device is good or bad. Then you have your adjustment, also called the calibration adjustment. We do this after we do the performance test. We're not going to adjust it before we take the reading. We need to let you know whether or not it was good or bad before it was adjusted. Uncertainty in measurement. This is our best guess at where that indicated value is and how close it is to the true value. So we know that we don't know everything. Traceability, this is all the steps it took to get from the reference calibration for our standards through our working standards down to your test equipment. And then finally, your test reports and certificates of calibration. That's the final report that says, hey, this device did this, it was good or not good. So we have resolution. Some devices have a lot of resolution, and some of them have not a lot of resolution. I like to use the little archery target here because the more rings you have, the more accurate your reading is. You have your precision. So this is your grouping of your measurements, how close all the measurements are to each other. So you get low precision or high precision. So you can be really, really precise, but not anywhere close to the center. So then you have your accuracy, which is your estimate from the indicated value to the true value. So these are two different multimeters. They have very, very similar functions. They have very, very similar resolution, and they have completely different costs. So we got a $180 meter versus an $890 meter. And if you look at all the specifications from the manual, you'll see that you have accuracies that are really close to each other. And I'm looking at just the 60 Hertz measurements here. So yes, you can have your different meters at different price points, and you'll have different costs associated with it. But in the end, your accuracies and your tolerances are going to be based off of what you need. So yeah, so you got different price points for different things and how you can get to what you're looking for. So again, this is where talking to your calibration laboratory before you purchase something can be very helpful, because most of your cal labs, they'll talk to you about, hey, yeah, if you're trying to measure 5 microamps, maybe this isn't the meter for you. You should probably be looking at something else, because this is something that we found is that people call us up saying, hey, you calibrated my device, it's not working. Well, what are you using it for? You're using the wrong device. So talk to us. Go ahead.
So I'll give you guys a great example. Some of you may or may not be familiar with ventilator analyzers out there, but at the end of the day, these companies are out there producing products that they also need to market and sell to you. So I'm not going to put any company's name out there on the spot, but there is a ventilator tester that shows a resolution of 3 decimals, so 0.000 essentially, with an accuracy of 0.05. We have another ventilator analyzer out there who has a resolution of 0.00, so only 2 decimals of resolution, but an accuracy of 0.02. I can tell you from a lot of experience, more of the units with the 3-point resolution have been purchased with the assumption that because of the third decimal point is more accurate, but that's false. The third decimal is actually irrelevant. They did it as a marketing ploy to catch people seeing, oh, it's got 3 decimals, I'm going to buy that one. So kind of our point to you guys is make sure that you're reading your specification sheets and that you find some of these marketing tools that they're using to help sell you on what you at first glance think might be a better unit than another one. Another example is an ESU analyzer that's out there that marketed itself as now having the capability of testing to higher current ratings. When you dig into the specification sheet, you'll find that there really was no difference between their previous model and the new model, other than that they just took the duty cycle and reduced it 50%. So by reducing the duty cycle, you now have a very short period of time to be able to do the testing of the ESU, which does allow for it to take more current before it gets too hot. But again, not really a good way of building a product, right? I think we'd all agree that you want a product that really can handle that capability, not just for a few seconds. But again, those are in the spec sheets, but you have to decipher those. So we're really encouraging you guys to take a detailed look at specification sheets, to DJ's point, and make sure that it is the right and appropriate tool for the job.
So NIST and traceability. So a lot of the requests that we get is that the devices are NIST traceable, which under the current ILAC agreement for interlaboratory calibration laboratories, we're not traceable to NIST, we're traceable to the SI, the international standard for the measurements. So I took this from the NIST QM1 because NIST has the best way to word this. So consistent with SIPM, and SIPM is the my French is terrible, but it's the
What was that?
I'm sorry. No. There NIST is the I'm sorry. The SIPM is the it's the Council International per Measurements, and my French is terrible on that, so I can't say it. I just call it SIPM. But so NIST measurements are directly traceable to the SI as realized and represented by NIST, or in rare cases, another national measurements institution. For those measurements like ambient temperature that do not provide a significant influence on overall measurement uncertainty, traceability can be attained from a Cal laboratory that is an accredited ILAC signatory. For some NIST chemical or material metrology measurements activities, metrological traceability to the SI is not possible. So in those cases, it's using consensus values. So in the case of, let's say, pH meters and conductivity, we can calibrate the meters themselves, but once you have the probes and you put it into the different solutions, the solutions are not technically a traceable measurement, because as soon as they're opened up, there's too many things going on and the solutions are not traceable. So what we have is a consensus agreement between our lab and the manufacturing lab or whomever for those chemical devices. It's our best guess that this is what it is.
How many of you guys are familiar really quick with SI or what the SI is? Does anybody understand what the SI is? Raise your hands way up there. Okay, so let's back up just so imagine a pyramid. You're going to have at the peak or pinnacle of the pyramid is the top. That is the SI, okay? So as a great example, the kilogram mass used to be, there was one primary mass that would sit at the very top of this, and it was owned and kept in France. You had references that were taken from that kilogram mass, and for example, 1 or 2 of them were given to NIST, a couple others were given to UCAS, which is the UK version of NIST, and they were distributed to the 8 organizations that NIST is part of around the world that all agree that we're all going to measure back to one, set value, if you will, okay? So then they would send in, let's say every 4 years, they would get together, they would bring in their references and compare them back to the 1 kilogram mass. Well, this was a big deal in science because about, what, 6 years ago now?
Yeah, 2018.
It was determined that the US or somebody in the US found something in nature to an atomic structure that was much more accurate than a physical 1 kilogram mass that we used to use. So it took years of agreement between these organizations to change from the 1 kilogram mass in France over to the atomic, because now everybody has the ability to use that atomic, value, and they don't need to come together every 4 years to compare their references to the 1 kilogram mass. They can all do it at any point in time back to that atomic value. And they can see, is my mass that we're comparing to, when I compare it to the atomic reference, are we in calibration or not? So it was a big deal. They moved it from the physical mass kilogram to that new standard. So there now is a new pinnacle for the SI measurement of mass. Okay. So moving down the chain, you have the 8 laboratories we talked about that are part of the agreement, NIST being one of them. They rest just below the SI. So they are the next most accurate compared to the standard itself. Everybody with me there? When you keep moving down, somewhere you're going to find that even your organization falls in this pyramid. You're just going to be down lower towards the bottom, because as we compare, again, you have to have something that's more accurate compared to something of less accuracy. And then that can be compared to something, again, of less accuracy as you move down the pinnacle. Does that make sense? So that's what we're talking about when we talk about an SI comparison, is what is the standard for mass or temperature or volts or resistance. Every one of those has a standard by which we compare for those measurements. Okay.
Yeah, talking about the international standards going up to the SI, there's 63 member nations in the SIPM, the consensus group. In 2018, all 63 member countries came together and finally agreed on one thing, and that was to change the kilogram over to using Planck's constant to measure mass. So we can't get our Congress people to agree on anything, but 63 countries agreed on changing the international standard for mass. So as you go up the traceability, as you move from your measurement instrument all the way up, your cost is going to increase as you get closer to NIST. It's just how, as you get smaller and smaller measurements, they take longer, everything, just that's the way it happens. As you move down the pyramid, your costs get lower, but you also gain in uncertainty, because with each step down, we have to import this uncertainty down to this one gets imported to this one. So it keeps adding all that uncertainty together. So a great example of an unbroken chain of measurements. You have your handheld multimeter, send it over to your Cal lab, they'll calibrate it. So we have an accuracy of 0.02 volts here at 10 volts. So here we have 37 parts per million at 10 volts. Move over to our direct voltage standard, we have 5 parts per million. Then you have your Josephson voltage reference, which uses the Josephson constant to measure an electron jumping across an array of like 18,000 arrays, and immersed in liquid helium at 3.7 Kelvin, so near absolute zero. And you have an accuracy of 15 parts per billion. And then those Josephson standards get intercompared every 5 years. So they'll send, the NIST Josephson standard and take those measurements and intercompare it with France, intercompare it with Japan. So this is where this gets really expensive really quick. So measurement uncertainty. Common uncertainties, we were talking about our common measurement uncertainties. So depending on what you're doing, you can have as little as 4 uncertainties, or you can have, depending on what's going on, 17 or 24 measurement uncertainties. I mean, the list, you can just keep going the smaller you try to measure. But your first one is your imported uncertainty, or your reference uncertainty from your time of calibration. Then you have your accuracy of your measurement reference, your resolution of your measurement reference, Then we start getting into your environment. If your temperature is swinging a lot, it's going to make your measurement swing a lot. Your setup and your stability. So depending on what type of multimeter leads you're using, you can actually impact your ability to measure smaller voltage readings with bad leads. And then finally, user errors. We're human, we all make errors, so it just happens. So routine calibration provides a level of confidence to perform to specifications for your service interval. So depending on how often you use your device, you may not have to get it calibrated every year. I mean, if you're only using it once a year, some things you just don't have to. But the more frequently you use it, the more often it should be calibrated. If you're using a multimeter every day, you're going to cause it to drift further than what the manufacturer's best guess was. So NASA did a 10-year study to figure out what are the most common errors attributing to out of tolerance conditions. One is the inherent nature of a device. So you can have some devices like gauge blocks that are made out of steel. They're going to rust. The more rust they have, the worse they're going to read. Your usage, again, back to that user error. Sometimes somebody's just going to drop something that's going to break. That's going to cause an out of tolerance condition. And transportation. So you can send something through UPS and it may just not survive its trip. So your metrology partnership with your Cal Lab, you should look for one that uses a quality management system that's similar to what you're doing or looking for something that you're looking for. Ensure your Cal Lab understands your applications and requirements. If you send your equipment over to a general purpose Cal Lab, they're going to do everything the same way every time. They don't care if you're Lockheed Martin or if you're, Jim Bob's automotive shop. They're going to calibrate everything the same way because that's the easiest way for them to do their business. Verify the services provided by your calibration laboratory. So once in a while, you're going to have to go back and double check. Did they actually calibrate my multimeter like a multimeter? We've seen calibration certs where it shows that it's a multimeter, but all of the report data showed that it was a torque wrench. It's like, but it's a multimeter. Why does it have torque values on a multimeter? I have no idea. So verify. Make sure that you're getting the service that you're paying for. So your payers and purchasers roles, of course, they're always looking for cost avoidance. But with that, you have with lower cost is not as great quality from time to time. Your service providers, again, they're not just there just to give you your calibration. Most calibration laboratories will help you. If you have a question like, hey, I got this new multimeter, I have no idea how to use it. It's got all these bells and whistles and I want it to do this and it says it can, but I just don't know. Your Cal Lab can probably help you because we see these things all the time. And the final thing here is your measurements transfer from your service provider to your biomed department and eventually to the patient floor. So make sure that what you're doing and the stuff that you're getting is working to support your end your in service. So anybody have any questions before we go into the practical side here? I know it's a lot of data really quick. All right, so up here at the front we have a little ice bath we made here. We have different types of measurement devices. So we have a high accuracy multimeter here with a SPRT temperature sensor. We have a platinum resistance thermometer here, and then we have some different thermocouple meters, and they're all measuring the same ice bath. And you're welcome to come on up. You don't have to sit there if you want.
Yeah, and let me give you a little background story on where this came from. So we get calls frequently, and I think with some of the regulatory that's coming around most recently, temperature, I don't know how many would agree with me, but temperature seems to be a hot topic lately. And so we will get customers that will call us, and I'll get a manager or director, and they get me and, hey, Dave, I kind of have a problem here. Okay, well, what can I help you with? Well, I've got, 7 thermometers sitting here on my desk. in a cup of water, and I've got an 8-degree difference across the board on all these thermometers. Okay, well, what's the problem? In their mind, they're thinking these should all
But I'm
read
trying to stir
the
it as
same,
well, too,
right?
so.
In my mind, I'm thinking, nope. And so then the questions begin. Well, you know, let's take the Fluke 52, for example, because that's, how many of you guys have a Fluke 52? I would say probably 80% of you in here have a Fluke 52. Okay, so the accuracy of a Fluke 52 meter, and I'm going to emphasize the term meter, is 0.3 degrees. Now, be honest, how many of you are aware that there's also an accuracy on the probe? Anybody aware that there? Okay, so here's where the problem starts. So in their mind, they're thinking there's a 0.3 degree accuracy of the Fluke 52 meter, which is absolutely correct. But now I say, well, what probe do you have plugged into it? Oh, I've got the little brown probe that came with it. Great. So that's got a 1.5 degree accuracy. So then it comes the next question. Well, what does that mean to me? Well, you need to add the 1.5 degrees of the thermocouple that you just plugged into it to the meter. So now that meter just became a 1.8 degree plus or minus, not even including any uncertainties that we've been just describing now. And I hear the, oh crap. Well, what's the matter? We've been using those for plasma freezers because they require 0.5 degrees. Oh, yeah, oh crap, you've got a problem because you've been using the wrong tool for the job. So again, these are the types of questions and things that we get brought to us on a daily basis that have really driven us to want to come out in more partnership with you guys to help you understand those are general metrology practices. Again, if nobody's teaching those in the biomed schools out there, these are some key fundamentals that are missing from you guys doing your daily jobs. So we're making our mission, because that is our daily job, to also partner up with you guys, whether it's through these classes or you guys calling us when you have a question, because again, it's all metrology at the end of the day. So now you've got a 1.8 degree swing on the Fluke 52. You've got, let's say, a Fluke 87. Anybody venture a guess on the temperature accuracy of a Fluke 87 multimeter? I mean, its primary function isn't necessarily temperature measurement. Yes, it has the little yellow, you know, thermometer on it, and yes, you could put it into temperature mode. But again, just because something reads temperature doesn't mean that it's the right tool for the job, right? So you've got about 1.5 degrees accuracy on that Fluke 87 before you even plug a probe into it. So let's say you plug the same thermocouple probe into the Fluke 87. You now have a 3 degree swing on a Fluke 87. So do you see where when somebody says, I've got 8 degrees of swing on all these various different, you know, devices out there, I don't necessarily see a problem with it, and they could all be in calibration based on each of their individual devices' accuracies and the probe that's being used with them, right? Does that make sense to everybody? So we also do an education back to, there is a NIST standard, and I happily email it probably weekly, that says, here's how to make an ice comparison bath. So number one, you need to have, and if you have, you know, that crunchy ice that everybody loves to chew on, right? You know, Sonic's got it and all that. Ideally, that would be the best ice to use. Because again, it's going to be able to get as close to all the other ice as possible with the smallest amount of water. Then you should have distilled water because it's got a specific gravity to it, right? And then you should put that into some kind of an insulated type of thermos or cup, and then it needs to be stirred constantly. Who wants to venture a guess why the stirring is important? Anybody? He was already talking to me earlier. So yes, you can build up thermal layers within even that mug, you know, ice water. And again, for the normal person, if you put a liquid and glass thermometer in there, it would probably read or look to read pretty on the dot. But when you start plugging in a PRT type probe that's reading in the 2 or 3 decimal range, it becomes very apparent that there are various thermal layers even in that ice bath. When you stir it, it now becomes a much more constant temperature throughout. And the way each of those probes, the bead probes, it's right at the very tip. But as you have PRTs, the way that they're built, you might have the first inch is where the actual measurement is. If it's a longer probe, you could have 3 or 4 inches worth of sensors in that probe. So it's really important to make sure that the bath that you've created is as stable of an environment with a constant temperature from low to high as possible. So by stirring it, you're going to create that environment for a more stable reading. So yeah, come on up now that we've given a little backstory and we've got some of those probes and things for you guys to be able to look at on here.
Right. How many people are familiar with the Vaccines for Children program, the VFC program? Okay, so the VFC program, for the requirements, it says that your temperature measurement device has to have an uncertainty of 0.5 degrees Celsius, right? So when we go back to, back here, when we talk about, your imported uncertainties down to what you're looking for, your temperature device, if your accuracy is 0.5 degrees, your uncertainty is going to be much wider than 0.5 degrees. You're going to be looking at closer to 0.8 degrees for your uncertainty. So with the VFC program, you need to keep that in mind, that just because the accuracy is 0.5, your uncertainty is going to be about 1.3, 1.4 times that with different effects and the imported uncertainty from the measurement reference. So this is where one of the reasons why we're out here is try to make sure that y'all understand that when they start talking about uncertainties, as biomedical and 1345 move closer to the 17025 style of measurement uncertainty, like all of this is going to play a role. So, and as I said, the NCSL RP6 committee, they're making their recommendations over to FDA for healthcare metrology, and we're trying to bring some of that up front before those become mandatory.
So we want to pick up and describe what we've got there.
So what we have here is we have Fluke 54 Series 2. It's a thermocouple meter. We have a Type K temperature probe. So the meter itself, the accuracy of your Fluke 54 or Fluke 52s, you're looking at 0 degrees. You're looking at 0.3 degrees for this, and your immersion probe is about 1.5 degrees Celsius. So you're talking a total error of about 2 degrees. It doesn't mean it can't measure down within 0.1. It's just that that's your measurement uncertainty, or your accuracy range is 2 degrees with the two together. We have an AM probe thermocouple meter as well. Its accuracy is really close to the Fluke 52, except for this one, we're using the air bead probe, and the air bead probe is 1.8 degrees. So now we have a little bit more than 2 degrees for our total error. We have a ThermalWorks platinum resistance thermometer. Its accuracy is 0.05 degrees Celsius. Its uncertainty is about 0.072, what we have. And then we have our Keithley digitizing DMM here. So this has the ability to measure temperature down to 20 millikelvin, and with the SPRT with it, we're looking at about 45 millikelvin. So each one of these have a different accuracy and different response times. So your thermocouple probes are going to be your fastest response because they're only trying to do a millivolt of change. So your response time with a thermocouple, usually under a minute, if not, some of them are down to 40 milliseconds. Your PRT probes are going to be a much longer response time, so you're not going to be able to see quick changes at all with them. Go ahead. Platinum resistance thermometers. So your PRT probes are usually response time of a minute to 5 minutes. So you're going to get an average temperature. You're not going to see sharp spikes. But the great thing is that they have a much tighter accuracy, usually a 1/10, if not 1/100th of a thermocouple. And then you have your SPRTs, and they're your special platinum resistance thermometers. And usually with those, you have a much wider temperature range that has a much tighter accuracy. This is how we get into the millikelvin measurements, but your response times are closer to 4 or 5 minutes for your measurements. So again, we're not looking for really quick measurements. We're looking for how stable it is over time. And with the graphing meter here, we can actually show you what the response curve looks like as we either shake or stir the pot and move the probe around to look at your different thermal layers. As we get closer to the ice, you'll see the response curve start to drop down. And which is the nice thing about your PRTs is because you have that average sensing. So you can see how it moves around and shifts.
And I'll give you guys a great example too. So I know a lot of shops will think, oh, that's got to be a really expensive, sophisticated piece of equipment there. Number one, we don't sell this, so this is not a plug for the equipment, okay? It's a Keithley DMM 6500 6.5-digit bench meter with the digitizing properties. The retail value is $1,200 bucks. The probe that we have plugged into it is a PRT. It's a high accuracy probe that's about $450 bucks. So for about $1,650 bucks, you've got a really accurate thermometer that can also do 6.5-digit voltage and AC DC current to 10 amps, high level resistance, a lot of other functions you might find. But compare that to some of the other handheld PRTs out there that all they do is 2 decimal PRT measurement at the same price range of $1,650 bucks. So the reason I make this point is because a device like that can have a lot of other uses in your shop besides just being temperature use, right? It could be used for a lot of other functions within your hospital for the same value as finding something of actually less accuracy that only can measure temperature. And again, those are some of the things that we like to try and help people out with is like, hey, did you know that these types of things exist? We use them for pretty high level stuff, but you know, you guys can also use them in your shop to expand your capabilities on different things as well. It's a DMM 6500 Keithley. Now, I will tell you, just like everything else, lead times right now are like 4 months. I don't know, like people have seemed to pick up that these things are out there for that kind of price range and have all these different capabilities. So I don't know if people are just buying them left and right or not, but I mean, it's pretty incredible what.
Yeah, and of course, there's other manufacturers that make a very similar product, usually with a higher
Agilent
price
has
tag.
one.
Yeah, Keysight's got their 34470 graphing multimeter, or 34460. Fluke has a variation of it as well. I mean, there's several out there.
Yeah.
It's just the main thing is making sure that what you're looking for and what you're going to use with it is to look at the specifications and see if it's got that function and if it's got that accuracy that you need for it. What I also recommend is if you are going to get a multimeter and a separate PRT, send them in together and ask the lab to marry them together because they can do that. They can actually chart it out with it, and they can give you a better calibration for you if you send them together and say, hey, I want this probe married to this multimeter, and get them both calibrated. So
yeah, it's like almost like a semi-permanent null, so that when you go to 0, 0 is, you know, as close to 0 as you can make it, so you can start right from there, which is great. And that shouldn't be charging you extra for that. That should be, you know, you'll get charged for the probe cal and the meter cal, but the putting the constants in there should not be an extra charge. Otherwise, just tell them, give me the constants from my probe, I'll plug them in. It's not hard.